Yesterday we saw that the multiplicative functions are closed under Dirichlet convolution, and today we are going to show that if A is multiplicative and if star G is multiplicative, then G must be multiplicative. That is proof. We prove by contradiction. That is, we assume that G is not multiplicative, and then we will proceed to show that if G is not multiplicative, this cannot be multiplicative. If G is not multiplicative, there exists pairs in N of integers, so that the GCD such that their GCD is 1 and G of N is not equal to G of N times G of N. So if M and N, if this pair could be chosen 1 and 1 1, if both are 1, then what is F star G at 1? This is F1 times G1, and you know that F1 is F1, so that is G1. But know that if this is equal to 1, that means G1 is not equal to G1 squared, right? That is, since G is not multiplicative and Mn is such a pair for which Gmn is equal to Gm times Gn is not holding, despite the fact that they are relatively prime. Okay. So if this is not true, then G1 in particular is not equal to 1. So what you get from here that this is not equal to 1. So F star G is not taking the value 1 at 1, and therefore this is not multiplicative. So now let's consider the case where M not both of M and N are 1, but choose M and N such that Mn is new. So now M is chosen such that GCD of N is not equal to 1. So this was the case where M and N move to 1. Okay. Now, this is just an example of the general case. What we are going to do is we are going to choose an M and N in such a way that they will be prime and M is minimum such that Gn is not equal to Gn times Gn. we are going to do, we are going to consider the value of f star g at Mn. Before doing that, note one thing, that if there are pairs of integers, so d prime, which are less than Mn, so if there exists, well, not if there exists, actually what I want to say is that for all d prime, for all d prime in N, for d prime is less than and GCD of d prime is equal to 1, you must have g of d prime is equal to d of d times g of d prime. Because this is the minimum thing for which this equality is not working. Alright? Any doubts?
GCD should be 1.
GCD? Yeah, actually we are trying to prove that G must be multiplicative. Okay? So this, I mean, if G is not multiplicative, then there is such a pair for which this doesn't hold. Gmn is equal to Gn. So here we are choosing Mn to have the minimum value for which such an equality is not true. Such an equality is not true. Okay? And now that means that for every d prime whose product is less than Mn, we must have the equality. Okay? So that's what we do. So consider this if star g at Mn is chosen in this manner. By definition, that is product over, well, f star g, since this is since Dirichlet convolution is commutative, f star g is the same as g star g, right? So you write this as g d prime is Mn by d prime. Of course, I'm writing g star f here. It's commutative. Okay? And what is here? D is dividing m, and d star is dividing m, and with the condition. Oh, there is no condition here because I mean this is the definition of convolution. Right? So note that for all the d and d prime, I mean all d primes as the d prime is less than Mn, this will we can write this as gd times d prime. But that's not the case when we take both d and d prime as equal to Mn. So we have a Gmn that is equal to summation d dividing m with d of g d is m by d. If is not given, that's given. This times summation d prime dividing m g d prime f of m by d prime, and here actually we have also split we are splitting the thing where this is gm and this is gm. That should not be allowed, right? So when is this equal to gm when this d is equal to 1. This d is equal to m, sorry. So the argument of f is equal to 1, that is 1. I mean, f of 1 is 1, right? It is 1. And what is happening here again, when this is n, this is 1, so f of 1 is 1, right? So that is gm times gm. That is a term which should not be here. Okay? And instead, what term was there? Where d and d prime both are m and n, right? So that was gmn here divided by fmn by fm. Sorry, mn by mn, that is 1. So that will happen just gmn. Okay? So here we must subtract the term m times gm and add the term gmn instead. Right? Okay? Now, can you tell me what is this thing? The first expression? This is g star f or f star g at n. And this is the same thing at n. Right? So this is what we are doing is that f star g at n is f star g at n times f star g at n minus gm plus gn. Again, recall that mn was a minimum term, so that gmn was not equal to gm times gn. So this one is not equal to 0. Right? That implies that if star gmn is not equal to f star gn times f star gn. Because this was supposed to be a multiplication. So,
since we assume that f is non-zero,
right.
in the previous class we had done something which is the inverse of it.
Right.
So, couldn't we just have multiplied f star g with f inverse on the left?
Yes.
And that would, and since it's closed, then that step on the
Right. That's a answer to indeed. Yes. So as a border we can use it. So here's the comment that just made. So yesterday there was a homework. Well, before we write the homework, just recall what was the group that we were considering yesterday. The group G. It starts the arithmetic convolution. These are the arithmetic functions. And this was forming a group. Then what?
This g1 is not.
Which one?
That because you were assuming g1 is not zero for the fact that.
Well, here we are just assuming that it is a multiplicative function.
Yes.
Divided by 0.
For this inverse,
Let's first define what is it, sir. The set of multiplicative functions. Functions, and you need to as just goes towards the thing, we should leave off the entire zero function from here. So A would be the set of multiplicative arithmetic functions, well, non-zero multiplicative arithmetic functions. Non-zero means that not entirely zero. I mean, actually, if one is zero, then everything turns out to zero. Well, what I mean is that M subset of G, which is I mean, so what I mean here, zero. So we are considering this set, that is the set of arithmetic functions which is not equal to zero, and we saw that f inverse exists in this one. And now consider in subset of G is that the functions in K are multiplicative. And also consider C subset of T such that functions in, well, not the functions in M, actually M is containing all the functions in J, which is one. The set of multiplicative functions in G and C subset of G, the set of completely multiplicative functions subgroup of and well, yesterday we saw that the inverse of mu is a unique function and the unique function is completely multiplicative but mu is not. Therefore, this one is not a proof. But how about this one? So, the answer to that we get from correlating this one. If well, sorry, G is an element, what we don't know here, we know that F is multiplicative, F not equal to 0 because it's a subset of M, and M is a subset of G. G is containing only the arithmetic functions with F not equal to 0. So it's already given to you that F is not equal to 0. It's a multiplicative function, and we know that F star, F inverse, we are defining F inverse immediately just for all the elements in G. So we know that F star F inverse is giving you I. If is a multiplicative function, then so is F inverse, because F star F inverse is equal to I, and F is given to the multiplicative function, a non-zero multiplicative function. So
formula that you gave me.
Sure, you can check directly, or you can just use this. So since I is a multiplicative function, that implies that F inverse must be a multiplicative function. So this is just a command proof. Now, we already saw that if there are functions and there are completely multiplicative functions which doesn't have completely multiplicative inverse. But can you say at least that completely multiplicative functions have multiplicative inverses? It turns out to be so. Moreover, we can write the inverses of completely multiplicative functions in terms of them and homogeneous functions. If is completely multiplicative, then if inverse is mu times f. So this is not due to convolution, this is times. So if inverse of n is mu and f. Just write it in that form. And proof is very simple. So at first, let's take this function. Let's just define some let g be a function from a to c, identity function of course. So let g from a to c be the function divided by g equal to mu n for all of this. Now what we are going to do here, we will compute the Dirichlet convolution of this with f. If star g n, this is going to give you summation, by definition, the sum of all the divisors of n if g n by d. Okay. And this is summation over. Okay, wait. Yeah, it doesn't matter. I mean, we would have also written it as gd times f n by d. And this is just mu d if d is of n by d. This we could do, of course, because again this is commutative. And note that f is completely multiplicative, that's given to you. Okay. So every times f of n by d is just f of n, which you can take out. And then the sum will be over summation mu t dividing n. Yeah, that is mu star u. It is I. That is what is f and im? It's just im, right? Because at n it is a multiplicative function. So f of 1 is 1 and I of 1 is 1. And for the rest of the things, this is 0. So you just remove the loop. And that means G is the inverse of f. Right? And now, suppose f inverse is given by this, that is, not suppose f inverse A is equal to and Fn for all n. And we must show that f is completely multiplicative. Okay? So, for a function with completely multiplicative, in particular, means that f of, so this is to show f of p times r, sorry, p power r is equal to, but it should be f of p whole power r, right? And that's nothing else because for any multiplicative functions, f of n is the product of such things, f of p r. Only for completely multiplicative ones, you can take the power out. So how do we proceed to show this? Well, we know that f inverse is given by this function, right? So on this one, if f inverse at p power r, that is giving you summation over if d if inverse. We have written down here already what it means, so we can just use that. So mu d is d of not n now, p power a r by d dividing R. So this is only non-zero for d equal to 1 and d equal to 2. So only those two cases are we write down here. So for d equal to 1, what we get? This is 1. This is we are assuming that f is well, we're not. So we're just assuming that this is equal to this. F of 1 times f of r
plus minus
f of p
and f of p r minus 1.
r minus 1.
In that
Okay, here we must also assume that f is multiplicative. So if is completely multiplicative,
oh,
then if f is completely multiplicative, if is completely multiplicative, p can only be if is multiplicative and this. And so the fact that f is multiplicative will ensure. Oh, and also here, when you have written that this will suffice, here we assume that f is multiplicative. That is it.
proving a converted.
Yes. Right. That is f of PR minus f of p times f of PR minus 1. this is the inverse of f, and if r is greater than 0, then this is taking value 0. Right? So that would imply that f of er is equal to f of t times f of er minus 1 for all r greater than or equal to 1. From which by that you can get this. So from which it follows that f of p power r is f of p therefore. Yeah, sure. So in particular, though the set of completely multiplicative functions is not closed under inversion, at least you get multiplicative inverses of the completely multiplicative functions. Here's a theorem or definition. Let G be multiplicative function of form G equal to summation mu with t divided n for some multiplicative function. Let's say this. Here was making excuse me, sir. So the proportion let f be multiplicative function then we have summation mu g with t d divided n is equal to the product of 1 minus t divided n. And this is rather straightforward. So since mu and f both are multiplicative, so is this function on the left. Gn right? So we are having mu and f multiplicative, and then the claim is that this function is going to be multiplicative as well. Why should be product? Well, yeah, at first you are having the product. What can you say about the product?
So this is mu f star u, right?
Mu,
This G is mu f star u.
mu f star
U.
Right, mu star, sure.
You have studied. Mu is multiplicative.
Yes.
Mu is multiplicative. F is multiplicative. So mu f is multiplicative.
Okay, yeah,
So
sure.
product.
Yes.
So mu f star u, that will also be multiplicative.
Sure.
So G is multiplicative.
So that means with small definition, have I defined summative function already?
Yeah.
Yesterday. So what you just said, it means that if a function is multiplicative, its summative function is also multiplicative, which we already proved yesterday. Instead of just using one function, we are using product function, which is by definition multiplicative. So that means now, since G is multiplicative, all you have to do is to check the values of G and the prime powers. Now consider G power. What is that? Summation G equals again. Summation P is in P power R. Mu G is B. Again, only the first two values will count, that is with the zeros. Yeah. So the first one is just mu1, f1, and f was given to be a multiplicative function, so it's 1. And the second one is just. So g of p here is equal to this, and then g of n is just a product of the price basis of this. So this is basically. So we meet again today in the evening at 7, and then we discuss the relation of the convolution with Dirichlet series.